Right, and we are asked to calculate the acceleration and to calculate the tension in the cable. So let's follow our strategy that we have now done in the previous examples for treating problems involving Newton's laws. First of all, we draw free body diagrams of all these objects. So let's start with mass M1. So the free body diagrams. So just remember again, only forces acting on an object are included. So if we look at M1, it's got mass, so it will be affected by gravity. So there's a force M1G downwards, and it's connected to the cable. If the cable were to snap, this mass would just drop like a stone. So there must be some force from the cable on the mass, and that force we know is just the tension in the cable. We're given that the acceleration, that mass M2, is accelerating downwards, which means that mass 1 must be accelerating upwards. But remember, because the cable cannot stretch, we know that whatever the magnitude of the acceleration of this object is, it has to be equal to the magnitude of the acceleration of that object. Because if this object covers a certain distance in a certain amount of time, it implies a certain acceleration. If that acceleration differs from that, this object would be able to cover a greater distance in a certain amount of time than this one would. So if this one moves 1 meter down the incline, this object has to move 1 meter upward to keep the length of the cable constant. So they have to be accelerating at the same rate. Which means we can write Newton's second law. So I'm just going to call this Newton 2. Says, well, the sum of forces must be equal to the acceleration. We know in this case the acceleration will be upwards. So we expect the tension to be greater in magnitude than the weight, because then the resultant force would be pointing upwards. So we've got that T minus M1G is equals to the acceleration. Now let's look at the second mass, mass 2. So I'm just going to draw in where the inclined plane would be. So there is mass M2. Now, this is the angle theta. Now, first of all, we know it's got mass, so it will have a weight, and that will just be equals to M2 times G, and it will act straight downwards. Now, remember, the normal force is always, if there's a surface that is the result of, that produces the normal force, that normal force must always be perpendicular to the surface. So the normal force must point in that direction in this case, because it's the force that prevents this mass from falling through the surface. It can slide up and down, but there must be some sort of force that prevents it from falling through the surface if the surface wasn't there, and that force is a normal force. Yes? Sorry? Oh, yes. Of course. This is just the sum of forces. M1A is, obviously a force. Thanks for that. Right, so we've got the weight, we've got the normal force, but we also know if the cable were to snap, this object would just slide down the surface unimpeded. So there's also a force from the cable. We know from the previous example just that tension must be equals to this tension, because it's a cable. The cable cannot stretch. So this is now our diagram. We know this angle over there will be theta as well. And remember, we said that for problems like this, we must always try to break them up into an x component and a y component. So if you've got an incline, it always makes sense to draw your y-axis to be perpendicular to the incline and to draw your x-axis parallel to the incline. This means the tension is now a force that's parallel to the incline, so the tension acts along the x-axis, so it's got only an x component. The normal force is perpendicular to the surface, so it's parallel to the y-axis, so that only has a y component. But the weight is now at an angle with respect to the x-axis, so it will have an x component that we can draw in over there, and it will have a y component that we can draw in over there. So we haven't changed anything physically, we've just chosen our frame of reference. And once we've chosen a frame of reference, we must be consistent. So I've chosen my frame of reference to be this, which means I can now break this force up into the sum of a y component, which I will call, let's call this wy, and an x component, which I will call wx. Now if we do this thing component by component in this frame of reference, we've got that for the x components. So now we only look at forces parallel to the incline. We know also, remember, our acceleration is in that direction. So if the acceleration is that direction, it means the forces pointing in the positive x direction must be larger than the forces pointing in the negative x direction. The only force we've got pointing in the positive x direction is the x component of the weight, which we call wx. That minus the tension must be equals to mass times acceleration, so m2 times a. If we look at this triangle, so I'm looking at this triangle over there. We've got that the x component can be related to this side, which is the hypotenuse, quite simply as whatever the weight of this object is, which is m2 times g, that's the magnitude of this, times the sine of theta minus t will be equals to m2 times a. And we can also look at the y components. For the y components, we've only got two. We've got the normal force, we've got the y component of the weight. There's no acceleration along the y direction. So they must completely balance. So we know that the normal force must be equals to the y component of the weight. The y component of the weight is related to this side, which I know, through m times g, sorry, it's m2 times g times now the cosine of theta. So if you look at this, we've got one equation in terms of the tension and the acceleration, and for the other object we had an equation in terms of the tension and the acceleration. So we can eliminate now for the tension. So if we write this in terms of tension, we've got tension is equals to m1a plus m1g. If we write this in terms of the tension, we get that the tension will be equals to m2g sine theta minus m2a. So we've got the same quantity, so we can equate this. So we can write these two equations as the same thing. So we've got m1 plus, well, we can write this as m1, so let's just keep it like it is. So m1a plus m1g is now going to be equals to m2g sine theta minus m2a. We can, remember we are asked to calculate for a. So if we write all the terms with a to one side, we've got a times m1 plus m2. So if I take that term, add that on both sides of the equation, I get this is equals to g times m2 sine theta minus m1. So I find that the acceleration is equals to g times m1 plus m2 divided by m2 sine theta minus m1. So we've got an expression for the acceleration.